Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 34th lecture. In this lecture, we will be discussing built-in self-test or BIST. Specifically, in this lecture, we will be looking at distinguishing features of BIST based testing and then its architecture, and then we will be looking at random test pattern generation and how test response is analyzed in BIST based testing. In the earlier lectures, we had looked into AT based testing, where AT stands for automatic test equipment. Now, AT based testing is very efficient in terms of that because it allows a high degree of automation, and also the quality of testing in AT based testing is very high because the fault coverage that we get in AT based testing, that is pretty high. So, AT based testing is very popular. However, AT based testing has got some disadvantages. And what are those disadvantages? The first is that the cost of testing is high. Why the cost is high? Because it requires an expensive automatic test equipment, right? So, the fixed cost is high for AT based testing. Additionally, the volume of data that is required in AT based testing, that is pretty high, and therefore the test time is also high, and therefore the cost of testing goes high, becomes higher in AT based testing. Another disadvantage is that the AT based testing can be done only in production environment, right? So, after we have done the fabrication of a die, we carry out AT based testing, right? But it lacks the capability of doing field testing, meaning that once we have fabricated our die, we have found that die to be good, and then we integrated it into a system, and that system is being used, and at the system level, if we suspect that whether our integrated circuit is working properly or not, so testing of the integrated circuit in the field or at the when the integration of a chip has been done at the system level, that is not possible for AT based testing. And another disadvantage of AT based testing is that it requires probes to apply the test patterns and also read the response out of the chip, right. So, but these probes have inductance and capacitances, and therefore we cannot carry out at speed testing for using in AT based testing. So, but some type of faults, for example delay faults, require that we do testing at speed or at a higher clock frequency, and those kind of testing are difficult to perform in using AT based method. So, as an alternative, another type of testing which is known as built-in self-test or BIST is also commonly used for integrated circuit. Now, in BIST what we do? In BIST we have test-oriented additional hardware and software features inside our integrated circuit. So, inside our chip we have some special hardwares and softwares which will do the testing of an IC internally, right. So, given an IC, the IC will do its own testing or test their own operation using the infrastructure of BIST or built-in self-test, right. Now, what is the advantage of it? It reduces the dependence on the external AT for testing, right. So, all the test infrastructure that is required for built-in self-test is contained within our design or integrated circuit, and therefore external is external patterns need not be applied and the response need not be read out of the chip, but those kind of the generation of the test patterns and the analysis of the response, those are done internally within our circuit. And this kind of testing or BIST the testing using BIST method is possible in field, meaning that once we have integrated our IC into a system and we suspect that whether our integrated circuit is working correctly or not, whether it has become faulty or not, we can run the BIST test infrastructure, and the BIST method will tell us whether our circuit is working fault free or it is having some fault, right. So, the testing can be done in the field also if our circuit has got the BIST infrastructure. Now, to have a BIST infrastructure within our design, it will require some cost in terms of hardware, meaning that it will occupy some area and so on, right. So, we want that the BIST infrastructure that we embed within our circuit, that is not taking a heavy cost in terms of area and in the infrastructure of the chip itself, right. Then if the BIST infrastructure itself takes a large amount of area, say on our die, then probably it is not cost efficient, right. And therefore, BIST method employs a special kind of methods so that the area overhead of embedding the BIST infrastructure is limited. And what are these extra features of BIST infrastructures? So, the first thing is that it uses or it contains pseudo random pattern generator inside the chip. So, these within our chip there are random pattern generators, and these patterns are actually used to test our chip. Also, these test vectors are dynamically generated and used while testing. So, what do we save in this case because of using pseudo random pattern generator? We save on the area, right, or we need not store a voluminous set of test vectors. For example, suppose we want to apply 1 million test vectors, right. Now, if we want to apply 1 million test vector, one method could have been we save all those test vectors in our chip, in our chip, in some ROM or so on. But then that ROM itself will be too big, and therefore the testing infrastructure will take so much area that it will not be efficient, right. So, by using pseudo random pattern generator, we are avoiding storing test vectors within our chip, but on the fly or dynamically it can generate those test patterns and those test patterns can be used for in the BIST method. And the second thing is that in the BIST method we do what is known as signature analysis. So, we do not compare the exact response that we get of our circuit with some golden response. Rather, what we do is that we derive a signature out of all the responses and compare only the signature obtained from our chip compared to the golden signature. And therefore, as a result, what do we save? We save storing, or we avoid storing voluminous expected response inside the chip. So, the test infrastructure is fully contained within our chip, but we are not storing test vectors, we are not storing the test response. What we do instead is that we have some infrastructure to generate pseudo random patterns, and also we do a kind of signature analysis. How these are done, we will see in the subsequent slides. Now, in BIST-based testing, as we have said, that it uses random pattern generator, or the test patterns are random, right. Now, an obvious question is that how good are random test patterns in detecting our faults, say stuck at faults, right. Now, if to assess that, we can plot the fault coverage of stuck at faults and versus the number of random test patterns. So, note that on the x-axis the number of the x-axis is logarithmic, right. Now, for many kinds of circuit we will see this kind of behavior or this kind of curve. Now, what can we infer from this curve? We can infer that the stuck at fault coverage rises to 100%. So, this is 100% logarithmical, right. And reaching 90% of the coverage or say 85-90% of the coverage is pretty easy. Say it will require say hundreds of patterns or in that range, right. So, what this curve or this observation tells us is that even if we use say random test patterns, then 85 to 90% of the stuck at faults can be covered, right. And therefore, the BIST based method or BIST based testing relies on random test patterns, right. So, it will not be able to cover 100% of the faults, right, but we can still get some fair idea that whether the faults are there in our circuit or not using just a few numbers of random test patterns. Now, let us look into the architecture of BIST, like how does a chip in which the BIST method has been implemented looks like. Now, this circuit under test is basically the main circuit part of our circuit which is delivering the functionality, and all other parts are basically showing the infrastructure which we need to add in our circuit to implement the BIST based method, right. Now, what are these extra infrastructures that we need to add? So, the first one is the test pattern generator, right. So, test pattern generator, it generates the test pattern for testing and it can contain also a small size ROM, right, to target some specific faults in our circuit. So, most of this test pattern generator will be a kind of random test pattern generator, but to target specific faults we can also use ROM to store some test patterns which we can also apply to our circuit and achieve a better coverage of the fault in the BIST based method. Now, depending on whether we are in the BIST mode, right, whether we are testing our circuit or whether the circuit is performing normal operation, there is an input selector, right. So, whenever we want that our circuit is tested, in that case the input will be selected from the test pattern generator, otherwise input will be coming from the primary input or say scan in, right. So, this so the input selector is a kind of multiplexer and it will be controlled by the BIST controller, right. So, when receiving the instruction from BIST controller, the input will be input selector will take the inputs from the test pattern generator and it will apply to the cut or circuit under test. Now, given the input, the circuit under test will produce an output, right. So, the cut may have some fault. In that case, the BIST infrastructure must be able to detect that fault, right. So, the output of this circuit under test goes to test response analyzer, right. So, test response analyzer, it generates signature for the test response and it compares, right. So, given the sequence of responses that will be received from circuit under test, test response analyzer will generate a signature and then compare it with the golden signature which is stored in its ROM. So, ROM contains only the golden signature, it does not contain the exact response that we expect from the cut, right. So, it only contains the ROM contains only the golden signature and therefore, the size of the ROM can be much smaller. So, given a large sequence of outputs that will be produced by the cut, the test response analyzer will somehow process that information and convert it into a signature, that is the test signature, right. That test signature, and then it compares with the golden signature which is stored in the ROM. Now, if the test signature and the golden signature match, we say that the circuit, the cut is not having a fault, and that result will be produced here, right. And in case the circuit, the cut was having some fault, then the signature that will be derived for the sequences produced by the cut, that will not match, or that is not expected not to match the ROM, and the or that is not to that is expected not to match the golden signature stored in the ROM, and in that case the cut has a fault in cut has been detected, and that output will be produced at the result, right. So, all these operations of the BIST based testing is controlled by this BIST controller, right. This is a BIST controller. It basically gives instruction to the test pattern generator that generate the test pattern, then it gives instruction to the input selector that select input from the test pattern generator rather than from the external world, and then it tells the test response analyzer to now process the information coming from cut and produce a golden signature, produce a test signature and compare with the golden signature and produce the result at the output, whether the cut is having a fault or not. So, all these operations are controlled by this BIST controller, and the strategy for overall test control is the most difficult part of the BIST, right. So, it is the responsibility of the designer to design this BIST controller, right. There are tools available that helps us in designing this BIST controller, but this is the most difficult part, that we might need to design an FSM which controls these operations in the proper sequence and then produces the correct result or the expected result at the output, right. So, a designer needs to design this BIST controller carefully. Now, let us look into how we can generate test patterns or random test patterns in BIST based testing, right. So, we typically use linear feedback shift register to generate random test patterns. Now, why do we use this kind of circuit, or why do we use a linear feedback shift register or LFSR? The reason is that it creates, or it is able to produce random test pattern that is repeatable, meaning that if we say that the LFSR is given a starting value or seed, then from that seed it will always produce the same sequence in the next clock cycle and so on, right. So, the test patterns that will be produced by LFSR will be repeatable, and an LFSR is a kind of circuit, or it is a kind of circuit which can produce the random test patterns very efficiently, and the area penalty that is required to implement LFSR, that is very small, right. And that is why we use LFSR in BIST, so that we can get a large number of random test patterns with the minimal area penalty. Now, how does a LFSR look like? So, in this figure I have shown a special type of LFSR which is known as standard LFSR, right. Now, in this LFSR, if we look carefully, then this is same as a shift register, right. So, whatever is the value at Q, it is going to the next flip flop, whatever is going to Q is again going to the next flip flop and so on, right. And so, this is a kind of a shift register. Only difference is that it has the first flip flop, or the flip flop whose output is labeled as AN-1. So, this flip flop is getting a feedback from other state elements, right. So, there is a feedback, and the feedback consists of logic gates, or consisting of XOR gates, right. So, we can tap the output of any flip flop to provide the feedback, right. So, this pink circles which are shown here, which are these indicates that whether we are tapping the output of the nth state elements in the feedback path or not. If we are tapping it, then we are saying that Hn minus Hi will take a value of 1. If we are not tapping, then we are saying that it is Hn minus 1 is taking a value of 0, right. Now, how can we understand the functionality of this LFSR? So, let us assume that in this LFSR that is shown here, there are n state elements. They are marked as A0, A1, An minus 2 to An minus 1. These are n state elements or flip flops, right. So, let us indicate their output or the value at the Q pin at the kth clock cycle as A0k, A1k, An minus 2k and An minus 1k, right. And then we can predict what will be its value in k plus 1th clock cycle, right. So, it is easy to see because it is a kind of shift register kind of structure. So, whatever will be the value of A1k, it will go to the next flip flop in the next clock cycle. So, A0 k plus 1, that is the value of A0 in k plus 1th clock cycle will be same as value of A1 in kth clock cycle, right. So, this will be true for all the flip flops A0 to An minus 2. But what about An minus 1 or this flip flop, right. This flip flop, the D pin is connected to a logic of XOR gates, right. And therefore, the whatever is the D at the D input, that will be become that will be value in the next clock cycle whenever the clock comes, right. So, the value of the nth flip flop or An minus 1, which is indicated here, right, for this flip flop in the k plus 1 clock cycle will be the XORs of A0k, right, the first one A0k and then A1k, assuming that H1 is there, then if it is being tapped, then we have H1 element, H1 this term will exist, right. And similarly, if S2 is this is being connected or this XOR gate exists, then S2 will be there and will take. So, this term will this XOR gate will contribute the term H2, A2k and so on, right. So, the last flip flop is taking the last flip flop An minus 1 flip flop is receiving the feedback from all other state elements, right. And this feedback or what will be the value? This will be the value that will be produced by this XOR, logic consisting of XOR gate. Now, these things will become more clear if we take an example. So, let us take an example of an LFSR. In this LFSR, there are only 3 state elements A0, A1, A2. So, first let us write its next state equation, right. So, for whatever the value was of A1 in the current clock cycle, that will go to A0 in the next clock cycle, right. So, A0 k plus 1 is A1 k. Similarly, what was the value in A2 in kth clock cycle, that will go to A1 in the next clock cycle. So, we will have A1 k plus 1 is equal to A2 k. Now, what about A2? Now, A2 is receiving at the D input the XOR of A1 and A0. So, we have A2 k plus 1, meaning that the value of A2 in the next clock cycle is whatever we have value of A0 in kth clock cycle XORed with whatever the value we have at A1 at kth clock cycle, right. So, this is the next state equation which we can write for this LFSR. Now, what will be the state diagram or how the states will be traversed for this LFSR? So, we can draw the state diagram using this equations, right. First, let us assume that the initial state of the LFSR is what is shown here 1 0 0, right. So, here we have 1, we have 0 here and we have 0 here, right. Now, in the next clock cycle, what will happen? Now, in the next clock cycle, this 1 for A2 will go to A1. So, we will have 1 here and this A1 that will go to A0 and we will have 0 here, right. And what will be the value of A2 in the next clock cycle? It will go, it will take a value which is XOR of these two things, right. So, XOR of 0 and 0, 0 XOR 0 is equal to 0. So, in the next clock cycle, what will the value of A2? It will be 0. So, if we start with 1 0 0, the next state will be 0 1 0, right. Now, if we assume that the next state is 0 1 0, similarly we can compute. So, if we assume that we have value 0 1 0, then in next clock cycle what will happen? This 0 will come to this 1 will go to this, sorry, 0 is going to this. So, here 0, this will go to 1, and what will the value of A2? It will XOR of 1 and 0, 1 XOR 0 is equal to 1. So, we will have 1 here. So, in the next state will be 1 0 1, right. So, this way we can see that how the states will be traversed for an LFSR, right. Now, interesting case happens if all the states are 0, right. Initial state, suppose all of them were 0, then what will be the next state? Now, this 0 will come here, we will have 0, this 0 will come here, we will have 0, and what will A2? A2 will be 0 XOR 0 is again 0. So, the next state of A2 will be also 0. So, if it is in a 0 0 0 state, it will get always stuck, right, and that is what it is shown, right. So, a 0 0 0 state is, all 0 state is a kind of a forbidden state for an LFSR, because if it gets into that, it will get stuck into it, right. So, however, if we choose the feedback logic properly, then we can get a long sequence of states in an LFSR, right. So, if there are say n elements in the, or in n state elements in an LFSR, then we can have maximum 2 to the power n states. Out of that 0 0 0 is forbidden, right. So, one state goes away. So, if we design properly our LFSR, then we can get these many numbers of states in a random manner. So, note that the states that we are getting here, then the 1 1 1 0 0 0 1 0, then 1 0 1 1 1 0 and so on. It is looking something a kind of a random pattern, right. It is not a kind of a counter or something, right. It is generated in a random pattern, random way, right. So, the for an LFSR, the test patterns generated by an LFSR have most of the properties of random numbers, right. So, that is one of the biggest reason that why we use LFSR for generating random test patterns in BIST based testing, right. And if it is desirable that we have a long sequence of test patterns, right, before it is repeating, right. So, it is desirable to have a long sequence of test pattern before being repeated, so that good fault coverage is achieved. And how can we do it? We can get a long sequence of random test patterns if we choose right number of n, say maybe 10, more than say 20 or 30 in that order. Then if we have a sufficient number of state elements in the LFSR, and also if we choose the feedback function properly, then we can have long sequences of random test patterns generated by an LFSR, right. However, some faults may not be covered by random pattern generator, right. Now, for example, just to give a sense of it, suppose there is an OR gate, right, and it is consisting of say 5 inputs, right. Now, if we want to test that whether the output is stuck at 0 or not, or rather stuck at 1 or not, right, then to detect this stuck at one fault, we must have a 0 at this output, and to have a 0, all the inputs must have a value of 0, right. All the 5 inputs must have a value of 0. Now, if we try to get these patterns of all zeros using a random pattern generator, then what will be its probability? Its probability will be 1 divided by 2 raised to the power 5 or 1 divided by 32, right. So, if by random test patterns, we may not be able to detect some kinds of fault, right. So, or it is very difficult to test some type of faults or test elements components in some type of circuits, and therefore, we can augment the test pattern generator with some deterministic test vector also, right. So, we do not rely totally on random test pattern generator, but we have a few test patterns which are derived using say ATPG tool, and those test patterns are stored in the ROM, right. So, and those test patterns will be applied also along with random test patterns in BIST based testing. Now, what will be the advantage of it? It will help us achieve high fault coverage with a small number of test vectors only. So, now how do we analyze the response that we obtained from our circuit under test? So, if say there are we are applying 1,000,000 test patterns, suppose there are 1,000,000 test patterns and that there are say 100 outputs, right, 100 output. Now, if we want to store all the responses in our circuit itself, then how much memory do we require? So, we will require 10 to the 100 million or 10 to the power 6 into 10 to the power 2, these many number of bits, right, and if divided by say 8, we will get number of bytes that we need to store. Now, if we think it will be or if we consider this number, it will be around 12.5 megabyte of memory. Now, this is too much of memory if we want to put it in our circuit, right, and it will require a large amount of area, right, and therefore, storing the response of our circuit within our circuit circuit which we are designing, that is impractical, right. So, what we do in BIST is that we use some method of compaction. So, what is compaction? Compaction is a method of reducing the number of bits in the circuit response. And how do we do compaction? We do it by using a statistical property of a circuit, and using that statistical property, we derive a signature, usually a number computed for a circuit from its responses, right. For example, suppose there were 100 million bits, right. Now, out of these 100 million bits that is in the output response, we just count the number of ones in those bits, right, for the golden circuit, for the circuit which is not having any fault, right, and treat it as a golden signature, right. And then when we do the BIST based testing, we do a signature analysis. We compute the signature of the good circuit and store it in the RAM and in the ROM in the BIST, and then compare it with the signature of a potentially faulty circuit. So, while doing testing, we compute the test signature. So, we compute say for example, the number of ones that we are getting in 100 million bits, right. That is the test signature, and we compare the number of bits that are expected to be 1 in the golden circuit or a fault free circuit. If those number match, we say that the circuit is good, else it is faulty. If golden signature matches test signature, then the circuit is assumed to be good. It is assumed to be good, else it is assumed to be, or else it is faulty, right. Now, the desirable thing is that the signature of a good circuit and faulty circuits must be different, right, but that is difficult to attain. right. So, and if they are not, the signature of good circuit and faulty circuits are not different, then what we say that aliasing has occurred. So, during testing it is possible that the signature of good circuit and faulty circuit match, right. If there is a good circuit and say number of ones is matching in the good circuit and number of ones are matching in a faulty circuit, right. If that matches, and then we say that aliasing is occurring, and in that case even though the circuit is faulty, we will not be able to capture that fault, or detect that the circuit is faulty, right. So, and why this detection, this aliasing occurs? So, the aliasing occurs because we are doing compaction, and this is a lossy compaction. This is not a lossless compression of the data. It is a lossy compression, meaning that out of say 100 million bits, we have found a signature, a compact signature, but we have lost a lot of information, right. We have lost all the information that what are the correct sequences of zeros and ones that will appear, right. And therefore, there is a loss in information, and that loss in information leads to aliasing. That is not a good situation, and we should avoid it, right. So, now how to compute the signature? So, one method can be ones counting, as I described, just count number of ones across all circuit responses, right. So, but what will the problem with this ones counting? Of course, there will be lot of aliasing, right. Why there can be aliasing? Because different permutation can yield the same signature. Suppose there were say 4 test vector T1, T2, T3, T4. The golden circuit was producing the output say 0, 0, 1, 0. So, the number of ones in the ones counting method in this case is 1, right. Now, suppose our circuit was faulty, but it was producing a response which is a permutation of it. For example, it was producing 1, 0, 0, 0, right. Now, in this case the number of ones is still 1, right. So, the responses are not matching, but the number of ones in the response is matching the fault free circuit, and therefore, we will consider these two circuits as fault free, which is wrong, right, and this occurs because of aliasing, right. So, ones counting is not a good method of computing the signature. So, how do we compute the signature? So, one of the techniques that we use in BIST based testing that for computing the signature is known as use with the help of modular LFSR. We again take help of LFSR. For example, there is another type of LFSR which is known as modular LFSR, in which the XOR gates are between two flip flops, right. So, let me show you an example. So, this is an example of a modular LFSR, right. And in this case, what we are in this, so this is the modular LFSR including the clock signal, right. So, this is the modular LFSR. In this case, what we are doing is that one of the XOR gates input from our cut, right. This is circuit under test, right. So, in this case, what happens is that the circuit will produce a sequence of zeros, ones, and that will go to the modular LFSR. It is called modular because this XOR gate is between two flip flops, right, in the between two flip flops, rather than it in the earlier example that we saw, that was standard flip flop, standard LFSR, in which XOR gate was external to the shift register, right. But here it is internal to the shift register, and it is known as modular LFSR. So, in this case the input will come the output produced by the cut will be going as input to the modular LFSR, and it will go on computing the signature, and after n clock cycle it will get a signature or the values at this these state elements, and that will be considered as the test signature, right. Now, this test signature can be computed for a fault free circuit, right, and that is considered as a golden signature, and that is stored in the ROM of the test response analyzer, and after n clock cycle when all the test patterns. So, here TPG is the test pattern generator. So, test pattern generator is generating random test pattern which is going as input to this cut, and after all the test patterns have been given to the cut, and the cut has produced the output and it has gone through the LFSR, the modular LFSR, a test signature will be generated, and that test signature is compared with the golden signature. If those signatures match, we say that it is passing. If they are mismatched and mismatched, then we say that the cut is having some fault, right. So, this is a structure which is known as single input signature register, right. So, why we use this kind of infrastructure, or why do we use modular LFSR in test response analyzer? The reason is that in this case the aliasing probability can be kept lower, right. So, the chances of aliasing is lower in this case compared to say once counting, and therefore, this kind of infrastructures are widely used, right. So, in this case another point to note is that we have to start with some seed value, right. We load these LFSRs or the state elements with some initial state, and then we start analyzing the response, right. Because from the behavior will be of an LFSR will be deterministic if we start with a seed value, a known deterministic seed value, and therefore, we must load the LFSR with a known seed value before starting the operation of this test response analyzer. Now, let us look into what are the advantages and disadvantages of BIST based testing. So, advantages is that it reduces the cost because we do not need expensive automatic test equipment, and we also need not store test patterns because we are generating it using test LFSR, right. And then we can do at speed test in BIST based method because we need not interface external signals for testing. And the other advantage of BIST is that we can perform testing in the production environment, right. We do not need expensive ATE, and after our chip has been integrated at the system level, we can still carry out BIST based testing, right. Now, what are disadvantages of BIST based testing? So, the first disadvantage is that it requires additional silicon area for LFSRs, for test response analyzer, and a BIST controller, and so on. And the area of our circuit will increase, and as we have seen earlier, the yield can come down and also reliability can decrease in a circuit in which BIST is implemented. There can also be performance loss if BIST infrastructures or added infrastructure comes in the critical path of our design, right. And the BIST based infrastructure will need some pins to indicate that whether now we are going into the BIST based testing, and also some pin or external port which will indicate that whether the BIST testing has passed or failed, and so on. So, the BIST based testing can require additional pins or ports in our design, and therefore, it may require bigger packages, right. So, these are some of the disadvantages. However, we still use BIST in our industrial designs, and the biggest advantage of BIST is that it allows us to do testing in the field, right, and therefore, BIST is very popular. Now, if you want to know more about BIST, I will suggest that you can go to these, or you can refer to these textbooks. Now, to summarize, in this lecture what we have discussed is the BIST architecture and what are the special features that we need to implement or we need to incorporate in our design to implement BIST based testing. Now, with this lecture we have covered all the topics that we wanted to cover related to design for test. From the next lecture onward, we will be looking into physical design. Thank you very much.